everyone, thank you so much for clicking onto the video. Today's learning objectives are to firstly understand that high-resolution proton NMR provides information about the positions of hydrogen-1 atoms in a molecule, and then to be able to use data from high-resolution hydrogen-1 NMR spectroscopy to predict the different types of proton present in a molecule given values of chemical shift, relate relative peak areas or ratio numbers of protons to the relative numbers of hydrogen-1 atoms in different environments, deduce the splitting patterns of adjacent non-equivalent protons using the n+1 rule, and hence suggest the possible structures for a molecule, and predict the chemical shifts and splitting patterns of the hydrogen-1 atoms in a given molecule. So now I'm going to talk about the background to NMR. And this won't actually come up in exam questions, but it's quite nice to know what NMR actually is. So NMR stands for nuclear magnetic resonance, and it's a very powerful tool for identifying compounds. And the basic principle behind this NMR lies in the fact that nuclei with odd mass numbers, so for example, hydrogen-1 or carbon-13, have a property called spin. And this means that they act as tiny magnets. So when we put these nuclei in magnetic fields, they can either align with the magnetic field, so we call this parallel, or against the magnetic field. And we say that this is anti-parallel. And a nucleus which has its spin aligned with the magnetic field has a lower energy compared to a nucleus aligned against a magnetic field. And there will be nuclei in both states, but there will be more in the lower parallel one. If the correct frequency of radiation is applied, some of the low energy nuclei absorb the energy and align themselves against the magnetic field. The nuclei then flips from one state to the other, and this is what we call resonance. And the part of the electromagnetic spectrum which corresponds to the energy needed to flip nuclei is radio waves. And this is what we call the resonant frequency. And a larger frequency corresponds to a larger energy gap between the parallel state and the non-parallel state, so the anti-parallel state. If the magnetic field is kept constant and the radio frequency is gradually increased, then different atomic nuclei will come into resonance at different frequencies depending on the strength of their atomic magnets. So just depending on that particular nuclei. And the energy difference between the aligned and non-aligned state depends to some extent on the environment. The resulting spectrum gives valuable information about the compound, and NMR is especially useful to find out about hydrogen atoms through hydrogen-1 NMR and carbon atoms through carbon-13 NMR. And these are the two types that we're going to look at. NMR has also many uses in medicine and also MRI machines, because MRI machines are a type of NMR machine. Now we're going to look at how NMR is done. So what happens is that the sample is dissolved in a solvent, and this is in a long, thin tube. And it's placed inside the machine where it's bombarded with radio waves in a strong magnetic field. And the stronger the magnetic field we use, the better the resolution of the signals, so the clearer they are. And the solvent we use is normally tetrachloromethane, CCl4, or CDCl3, which is the deuterated version, which just means that we've replaced a chlorine with deuterium. We also need to calibrate the spectrum, and this is done by adding a small quantity of tetramethylsaline, or TMS, to the samples, and this produces a single peak at 0 parts per million, and we're going to look at what that actually means a bit later, providing an internal standard to which the other peaks are compared to. So the actual formula for tetramethylsaline is a silicon attached to 4 of these methyl groups. So this is our TMS molecule. And so this only produces a single peak at 0, and so we can use this as our standard. And there are a few reasons why we use TMS, and you'll need to memorize all of these. So the first is that it gives only one signal, it's non-toxic, it's inert, and it also has a low boiling point, and so it can be easily removed from the sample afterwards. And the last thing which makes TMS good to use is that it gives a signal which is much further right than most of the signals from the organic compounds. So if we're going to look at this example of a spectra on the right, this peak here at 0 parts per million is our peak for TMS. And so we measure all of the other peaks in comparison to this peak, so how far away they are from this peak. So now I'm going to introduce chemical shift. And so the spectra are recorded on a scale known as the chemical shift. And we denote this using the Greek letter delta. And this is basically how far the signal is away from the signal for TMS, which is our standard, in parts per million. So we have that TMS has a peak at 0 parts per million. And so this is our standard. Most signals are between 0 and 10 parts per million away from the signal for TMS, and a scale is usually shown on the x-axis. The nuclei in a molecule are shielded from the magnetic field by their bonding electrons. And this means that they feel an effective magnetic field smaller than the actual field. And one really important thing to know is that nuclei in different positions have different levels of shielding, and therefore they're in different environments. So basically they feel different forces from this magnetic field. And the general rule we have is that the greater the electron density around the nuclei, the smaller the magnetic field felt by that nucleus, and the lower the frequency at which it resonates. So basically the smaller its chemical shift. And so in the data booklet, you should have either a more mapped out diagram like the one on the left, or a table like the one on the right. So we would have delta, which is the chemical shift, measured in parts per million on the x-axis. And then we see TMS here is our standard, so it's at 0 ppm. So now we're going to have a look at NMR spectra. And so the spectrum contains a series of signals or peaks showing where the compound absorbs radio waves. And the horizontal scale is the chemical shift. And this indicates how far each signal is shifted away from that for tetramethylsaline or TMS, which is our standard. And this is at 0 ppm or parts per million. And the vertical axis represents the energy absorbed. So from NMR machines, we can form these graphs which have the energy absorbed over the chemical shift. And so here we have two examples of NMR spectra. So on the left we have a proton NMR, which is H1. So it's hydrogen with one proton. And on the right we have a carbon-13 NMR. So now we're going to look at another type of NMR, which is proton NMR or hydrogen-1 NMR. So it is much easier to get a proton NMR compared to a carbon-13 NMR, as there are more hydrogen atoms in molecules compared to carbon atoms. And the chemical shift for proton NMR depends on what atoms or groups are near the hydrogen. And so just like in carbon-13 NMR, the nuclei with more electrons surrounding them feel less of the magnetic field, and so they'll have a smaller chemical shift. And also, like in carbon-13 NMR, each peak corresponds to hydrogens in different environments. So what determines how many peaks we have is how many hydrogens we have in different environments. And the values of chemical shift in proton NMR are significantly smaller than those for carbon-13 NMR. And most are actually between 0 and 10 parts per million. And again, the reference peak is taken as 0 ppm, and this is the peak for TMS, tetramethylsaline. And so we have the formula of tetramethylsaline, which is silicon attached to 4 methyl groups. And so we can see that we have 12 of these hydrogens. And by definition, we set all of these hydrogens at 0 ppm. So because all of these 12 hydrogens give one signal, because they're all in the same environment, they're all singly bonded to a carbon, which is singly bonded to a silicon, we get one peak for all of these hydrogens, and this peak is taken to be 0 ppm. And also, high-resolution proton NMR provides information about the positions of hydrogen 1 atoms in a molecule. And so at the bottom, we have an example of a proton NMR spectra. Now we're going to look at integration trace. So this is only present in hydrogen 1 or proton NMR. It doesn't come up in carbon-13 NMR. So in proton NMR spectra, the area under the peak is related to how many hydrogen nuclei are in that particular environment. And that's something really important to remember. So we have that the area under is related to how many hydrogen nuclei we have in that particular environment. So for example, in the spectrum of methanol, which is CH3OH, if I draw that out, so we have a carbon with 3 hydrogens, and then we have an OH. So we have 4 hydrogens in total, but these 3 here, like for carbon-13, these are all in the same environment because they're all attached to a carbon which is singly bonded to an oxygen. And then this other hydrogen here, this one, is in a different environment. And so the peak for the CH3 will be 3 times the area of the OH peak because we've got 3 hydrogens rather than 1. And this can be really difficult to evaluate by eye, and so the NMR instrument produces a line which we call the integration trace. So if we have a look at the spectra on the left, the red line is the integration trace. And the relative heights of the steps of this trace give the relative number of each type of hydrogen, which is 3 to 1 in this case. But sometimes, for simplicity, the relative number of hydrogen atoms that each peak represents will just be written on each peak. So instead of having this integration trace, we'll have something that looks like the spectra on the right, where we'll just have the relative numbers labeled on each peak. And now we're going to talk about spin-spin coupling. So this only happens with proton NMR as well. So if you zoom in on most NMR peaks, they are split into particular patterns, and this is called spin-spin coupling. And this happens because the applied magnetic field felt by any hydrogen atom is affected by the magnetic field of the hydrogen atoms on the neighbouring carbon atoms. And spin-spin coupling gives information about the neighbouring hydrogen atoms of one hydrogen atom, and so this can be really helpful when working out the structure. And so we have a rule, and it's called the n+1 rule. And it states that n hydrogens on an adjacent carbon atom will split a peak into n+1 smaller peaks. And so, for example, if we have one hydrogen atom on an adjacent carbon to the hydrogen we're looking at, this will split the NMR signal of a particular hydrogen into 2 peaks, each of the same height. And this is what we call a doublet if there's 2 peaks. So there are 4 couplings that we need to know about. And the first is a singlet, then a doublet, a triplet, and a quartet. And sometimes we can use a multiplet if we have more than 4 peaks. So we have a diagram on the right of each of these couplings. So a singlet is just 1 peak, a doublet is 2 peaks, a triplet is 3, and a quartet is 4. So the singlet is caused by having 0 hydrogens on the adjacent carbon. And then a doublet we've seen is caused by 1 hydrogen on the adjacent carbon. and then a triplet would be 2, and then a quartet would be 3. So now we're going to look a bit more in depth about the origin of couplings. So first, let's consider the NMR spectrum of CH2Cl, CHCl2. So drawing out this molecule, we can see what kind of spectrum we would get. So we have 2 carbons, and then we have a chlorine attached to this one and 2 chlorines on this one. And then we have hydrogens everywhere else. So now looking at the hydrogens, we can see that both of these hydrogens are in the same environment, and this hydrogen here will be in a different environment. And the way we tell this is exactly the same as how we would look at carbon-13 NMR. So you just look at what these hydrogens are attached to, and then what the carbons they're attached to are attached to themselves. So the 2 yellow hydrogens are both attached to a carbon, which is singly bonded to a chlorine and another carbon. However, the other hydrogen is attached to a carbon which is bonded to 2 chlorines and a carbon, and so it's in a completely different environment. And now what we see is we have 2 different peaks because we have 2 different environments of hydrogens. And now to find out the couplings, we then look at the hydrogen next door. So for the 2 yellow hydrogens, we look at the adjacent carbon, which is this carbon here. And this carbon has 1 hydrogen on it. And so for the yellow hydrogens, we get a doublet peak. And that's because we have the n+1 rule. So we have 1 hydrogen on the carbon adjacent, and so we create we have 2 peaks. And then for the green hydrogen, we must have a triplet peak because we have 2 hydrogens on the carbon next door. So this is a triplet. And one really important thing to remember is that peaks in an NMR spectrum are in different places, and this is due to hydrogens experiencing different magnetic fields due to their different environments. And so this is going to help us explain why we get doublets and triplets and also quartets. So firstly, looking at the doublet. So this is formed from the CH2 group. So the CH2 group forms a doublet. And 2 peaks close together suggests that these 2 hydrogens feel 2 slightly different magnetic fields. And this is due to the hydrogen, the green hydrogen that we have, which is on the adjacent carbon. And this is because the hydrogen next door has its own small magnetic field. And depending on how it's aligned with the magnetic field, it can either strengthen or weaken the field felt by the CH2 group. And so if we have the magnetic field like this is the magnetic field. And if we have the adjacent carbon, so the one which is highlighted in green, aligned with this magnetic field, this will make our fields, this will make the 2 hydrogens on the CH2 group feel slightly stronger magnetic field. So this will make it stronger. So that's the first thing that can happen. But we can also get that the hydrogen will have a magnetic field which is aligned against the magnetic field. So again, we have the magnetic field here. And if it's aligned against, then that means that the CH2 group will feel or feels a weaker field compared to what it would be if we didn't have any hydrogens on the carbon adjacent. And there's an equal chance of either one of these arrangements happening. And so there'll be 2 peaks for the CH2 group, so a doublet, and equal areas under them. So that's why we get that doublets look like this in the ratio 1 to 1. However, for the triplet, the CH hydrogen must be feeling any one of 3 slightly different magnetic fields, because we've got 3 peaks now instead of 1. And so we get 3 different arrangements. The first one we can get is if we have the external magnetic field, and we have both of the 2 hydrogens on the adjacent carbon aligned with this field. So we can get this. And this means that the CH group feels a stronger field. So when I say CH group, what I really mean is that hydrogen on the CH group. And then the second thing that can happen, the second arrangement we get, is if we have the magnetic field and we have one being aligned with the magnetic field and one being aligned against the magnetic field. However, we can also get it the other way around. So we could say that the other one was aligned against, and the other one would be aligned with the magnetic field. And so with both of these arrangements, we have that the CH group feels the same field because they cancel out. And then the final arrangement we get is if we have a magnetic field and we have both of them aligned against this magnetic field. So then again, what we get here is that the CH group feels a weaker field. And so we can see the areas under the peaks will be in the ratio of 1 to 2 to 1, because we have double the chance of the CH group feeling the same field compared to feeling a stronger field or a weaker field. So that's why for triplet peaks, we have 3 peaks, but they're in the ratio of 1 to 2 to 1. So the one in the middle will be double the height of the other 2, and so they're in the ratio of 1 to 2 to 1. And this same principle can be applied for looking at the origin of quartets. So what we have for quartets is that just looking at the arrangements that we can get. So again, we have a magnetic field. And so the first arrangement we can get is if we have all of them aligned with this magnetic field. So we have 3 of them aligned. And then the second arrangement we could get would be if we had, and so if we had this one and this one aligned and this one not aligned, or we could have this one going up and this one going down and this one going up, or we could have this going down and these 2 going up. We could also get, if we had the magnetic field again going up, two of them not being aligned with this magnetic field. So again, we have another 3 arrangements, another 3 ways that we could get this arrangement. And then the last one would be if we had all of them not being aligned with the magnetic field. So if we had all of them going down. And so we can see that we would have 4 different peaks, but we'd have a ratio of 1 to 3 to 3 and then to 1, because we have 3 ways in which we can get either 2 aligned with the magnetic field or 2 aligned against the magnetic field, and only one way that we can get all 3 to be aligned with the magnetic field and all 3 to be aligned against the magnetic field. So this one on the left will make the adjacent hydrogens feel the strongest field. And then going down, this one would create the weakest field. So that's why a quartet peak will look like this. It'll be in the ratio of 1 to 3 to 3 and then to 1. So now we're going to have a look at how to justify proton NMR spectra. So here we have the spectra of propanoic acid, and we're going to just go through why we have all the peaks where they are and also the splitting. So firstly, we're going to draw out propanoic acid. So we have CH3, then CH2, and then we have the C double bond O, OH, which is the carboxylic acid group. And now we're going to look at the hydrogen. So this is very similar to carbon-13 NMR. So we look at the hydrogens and see which ones are in the same environments and which ones are in different environments. So we can see that this hydrogen, and also this hydrogen, these are all in the same environment because they're all singly bonded to a carbon, which is singly bonded to another carbon. And then now when we look at these two hydrogens, they are both in the same environment as each other because they're singly bonded to a carbon, which is then bonded to a CH3 and then a carboxylic acid group. And then finally we have this hydrogen, which is in a completely different environment to all the other 5 hydrogens because it's attached to an oxygen. And so we should have 3 peaks because we have 3 different environments. So now we're going to use our data booklet to work out where all these peaks should be. So first looking at the yellow hydrogens. So these yellow hydrogens are attached to a carbon, which is attached to another carbon. And so this is like an alkane. So we look at this box here. And so the chemical shift value will be between 0 and about 1.8. So we have 0 to 1.8 ppm. And so now we move on to the green hydrogens, and these green hydrogens are attached to a methyl group and then a carboxylic acid group. And if we look at our data booklet, we see that this box here is the one which matches our environment the most because we have a hydrogen which is attached to a carbon, and this carbon is then attached to a C double bond O. And so its chemical shift value will be probably between 1.8 to about 3. And finally, looking at the last hydrogen, we have that this hydrogen is attached to an oxygen and it's a carboxylic acid. And so this is the box that we're looking for. And so its value will be between 10 and 12 ppm. And now we've worked out where our 3 peaks are, now we have to look at splitting, because unlike carbon-13 NMR, we get splitting with hydrogens where we have the n+1 rule. So if we have one hydrogen on the carbon adjacent to the hydrogens that we're looking at, then it will form a doublet, so 2 peaks. So first looking at the yellow hydrogens, if we look at this adjacent carbon here, we have 2 hydrogens on this carbon, and so that means that we form 3 peaks, so we get a triplet. And then now looking at the green hydrogens, we have this carbon next door, which has 3 hydrogens on it, and this carbon doesn't have any hydrogens on it. And so we get a quartet because the carbon on the left has 3 hydrogens. And then finally, looking at the last hydrogen, this isn't attached to any carbons, and so this will just be a singlet peak. And we could also look at the different areas we have under each peak, because for the yellow hydrogens we have 3 of them, and so the relative intensity of it will be 3. And then for the green hydrogens we have 2, so the relative intensity is 2. And then for the last hydrogen we only have 1 of them, so the relative intensity is 1. And so we can work out, well, we can write down the relative intensity. So the relative intensity of signals is equal to 3 to 2 to 1. So it's basically just telling us that we have 3 hydrogens which are yellow, 2 which are green, and 1 which is blue. And so now we can look at our spectra and justify why we have everything where they are. So firstly, looking at the yellow hydrogens. This should form 1 peak, and it should be a triplet peak, and it should be between 0 and 1.8. So we can see that this peak here is exactly that. So we have a relative intensity of 3, meaning there's 3 hydrogens. And it's also a triplet because it's got 3 little peaks in that 1 peak. And it's also at about 1.2. So that is between 0 and 1.8 ppm. And so this peak must represent these 3 hydrogens. And now looking at these 2 hydrogens, they should form a quartet peak with a relative intensity of 2. The value of the chemical shift should be between 1.8 and 3. And so we have this peak here, which is at about 2. And so this is the peak which represents these 2 hydrogens. And we can also see that it's definitely a quartet because we have 4 peaks within that 1 peak. And we have that relative intensity of 2, which is marked on here. And then finally, looking at the last hydrogen, we should have a singlet peak at around 10 to 12 ppm, and the relative intensity should be 1. And that's exactly what we have here. And so this peak must be the one which represents this hydrogen. So we've now justified why this spectra is the way it is. So now we're going to have a look at how we predict proton NMR spectra. So sometimes we're not given the spectra to look at, and we're asked to predict the spectra instead. And so the first thing we do is draw out the molecule. So we have methyl propene, and so that's propene with a methyl group. So that must be on the 2nd carbon. So we have a CH3, and then we have a carbon with a methyl group, and then a double bond, and then a carbon with 2 hydrogens. And now we look at the hydrogens and see which ones are in the same environments and which ones are in different environments. So firstly, we're going to look at these hydrogens here. So we can see that these 3 hydrogens and also these are in exactly the same environment because they're all attached to a carbon, which is then attached to this carbon here. And so all of these 6 hydrogens are actually in the same environment. And then looking at these 2 hydrogens, these are in the same environment as each other, but different to the other 6 because they're attached to a carbon, which is then directly attached to a double bond. And so because we have 2 different environments, we have 2 peaks. And so firstly, looking at the green hydrogens. And so firstly, looking at the green hydrogens, we have that these carbons are attached to a double bond carbon. And so looking at our data booklet, we'll be able to find out that these hydrogens will have a chemical value, so the peak will have a chemical shift value between 4.5 and 6. So normally you would write it out like we did for carbon-13, so write out the structural formula and then highlight the hydrogens. But because I'm using colour, we don't need to do that. And then for the yellow hydrogens, if we look at the data booklet, this peak should be around 0.7 to 1.2 ppm. because it's basically classed as a hydrogen which is bonded to a carbon and then to an R group. And then now we need to look at our splitting. So firstly, looking at the green hydrogens, we look to the adjacent carbon, and this carbon actually doesn't have any hydrogens on it. And so this green peak must be a singlet because we don't get any splitting. And now we look at the yellow hydrogens, and then we look to the adjacent carbon, which is the one I've underlined in purple again. And this is the same carbon we looked at before, and this also doesn't have any hydrogens on it. And so this is also a singlet peak. And now we can look at our relative intensities. So we have 6 of the yellow hydrogens and 2 of the green hydrogens. And so we must have a ratio of 3 to 1. So we find the simplest whole number ratio. So what we have here is the splitting, and then we have the relative intensity here. And so this is how the spectra would look. And then now we're going to move on to butene. So we have 4 carbons in the main chain, and then a double bond between the second and third carbons. And then we have hydrogens everywhere else. And now we look at the hydrogens again and see which ones are in the same environments and which ones are in different environments. So we can see that these 3 are in the same environment as these 3 because it's a symmetrical molecule. And also because it's symmetrical, that means that this hydrogen is in the same environment as this hydrogen. And so again, we get 2 peaks because we have 2 different environments. So firstly, looking at the green hydrogens, these hydrogens are attached to carbons which have a double bond. And so this peak will have a chemical shift value between 4.5 and 6. So always remember that to find all the chemical shift values, you have to look at your data booklet. And then for the yellow hydrogens, their chemical shift value will be between 0.7 and 1.2. And then now we look at the splitting again. So firstly, looking at the green hydrogens, we look at the adjacent carbon, so basically the 2 carbons on the outside, and they both have 3 hydrogens on those carbons, and so we must have a quartet peak due to the n+1 rule. And then looking at the yellow hydrogens, we have next door 1 hydrogen on the adjacent carbon, and so we must have a doublet peak. And now looking at the relative intensity, we have 6 of the yellow hydrogens and 2 of the green hydrogens. And so again, we must have a relative intensity ratio of 1 to 3. And now looking at propanones, so again, we do exactly the same thing. So we have CH3, and then C double bond O, and then CH3. So again, this is a symmetrical molecule, and so these 6 hydrogens will all be in the same environment. And so that means we only get 1 peak for this spectrum. And so for this peak, we have that these hydrogens will have a ppm value 2.1 and 2.6. And now if we think about splitting, so if we look at this carbon, for example, so we're looking at the yellow hydrogens and we're looking at this carbon. What we do to find out the splitting is look at the adjacent carbon, which is this one here. And we see how many hydrogens are on it, and we use the n+1 rule. And because this carbon doesn't have any hydrogens on it, that means that there is no splitting. And so we get a singlet peak. And we don't have any relative intensity because we can't compare this peak to any other peaks. And so we just put not applicable. And then finally, looking at dimethyl ethyl propanoate, this is an ester and it's made up of dimethyl ethanol and propanoic acid. So first we draw out the propanoic acid section. So we have CH3 and then CH2. Then now we have the carboxylic acid, so we have COO. And now we add on our alcohol. So we have dimethyl ethanol. So that's a carbon chain of 2. And then we must have 2 methyl groups on the second carbon. And then 3 hydrogens on this outer carbon. So this is our molecule. So again, the first thing we do is look at all the different environments we have. And first of all, we can see that these hydrogens are in the same environment as each other. And they're also in the same environment as these hydrogens and these hydrogens. And this is because they're all attached to this carbon here, which is then attached to an oxygen. And then if we look at these 2 hydrogens, they are in the same environment as each other because they're attached to a carbon with a methyl group and then an R group. And then finally, if we look at these 3 hydrogens, they are all in the same environment as each other because they're all attached to a carbon, which is then attached to an R group. So because we have 3 different environments, that means we have 3 peaks. So firstly, looking at the pink carbons, so their ppm value will be between 0.7 and 1.2. And then looking at the green hydrogens, we have a ppm value between 2.1 and 2.6. And then looking at the yellow hydrogens, we have a ppm value between 0.7 and 1.2. So again, now we look at their splitting. So firstly, looking at the pink hydrogens, on the adjacent carbon, we have 2 hydrogens, and so this must be a triplet peak. And then looking at the green hydrogens, on the right-hand side, this carbon doesn't have any hydrogens on it. But on the left-hand side, we have 3 hydrogens on the adjacent carbon, and so this must form a quartet peak. And then looking at the yellow hydrogens, if we look at the adjacent carbon, there are no hydrogens attached to this carbon, and so this must be a singlet peak. And now we can look at their relative intensities. So we have 3 of the pink hydrogens, 2 of the green hydrogens, and 9 of the yellow hydrogens. And so this is the lowest whole number ratio we can have. So we have 3 to 2 to 9. And so in conclusion, in order to predict NMR spectra or proton NMR spectra, the first thing you do is draw out the molecule, and then you find all the hydrogens which are in the same environments or different environments, and this will tell you the amount of peaks you have, depending on how many environments you have. And then what you do is you look at your data booklet and find out where all these peaks should lie. And then we look at splitting. So you look at the adjacent carbon and then you add 1 to however many hydrogens you have on that adjacent carbon. And then finally, you look at the relative intensities. So you basically count up how many carbons you have of each in each different environment, and then find the simplest whole number ratio. You'll also need to know how to predict the structure of compounds using its NMR spectrum. And so firstly, we're going to look at some common signals that you can look out for that will make it a bit easier for you to find the structure. So firstly, we're going to look at the ethyl group. And how to identify that you have an ethyl group as part of a compound is that you'll get a triplet peak and a quartet peak. And this will be in a ratio of 3 to 2. So 2 rules that we have with these 2 peaks are that the triplet and quartet peak do not have to be next to each other in the spectrum. And also, the atom that is joined to the other side of the CH2 can't have any hydrogens on it unless they don't couple. So, for example, the OH group or an equivalent CH2, as in butane. So how this works is that if we have a CH3-CH2 group, these three hydrogens here, they will produce a triplet peak because we have two hydrogens on this adjacent carbon here. And so that means that these two hydrogens will produce a quartet peak. And this is due to the three hydrogens on the adjacent carbon. And so the relative intensity of these will be 3 to 2 because we have three hydrogens on the first carbon and two hydrogens on the second carbon. And the reason why we can't have anything on the other side of this carbon here is because then we wouldn't have a quartet, because we would have a quartet due to. But if we had, for example, a CH2 group on here, and then, for example, we had a carboxylic acid, then these two hydrogens would then also have an effect on our hydrogens, and so it wouldn't form a quartet peak anymore. It would be a multiplet because we have three hydrogens on the left of it, on the left adjacent carbon, and on the right adjacent carbon we have two hydrogens. And so that's why we can't have anything with a hydrogen on it on the right. However, we can have a CH2 and then CH3, as in butane. Because if we have CH2 and CH3, these two hydrogens will also be in the same environment as these, and so we'll still have that quartet peak. And secondly, we're going to look at the CH2-CH2 group. So this will form a triplet and a triplet in a relative intensity ratio of 2 to 2. And the rules are that these two triplets do not have to be next to each other. And the two CH2 groups must be inequivalent. And this is because if they were the same, so if they had equal things on the other side, then we would have one signal for all four of these hydrogens instead of one signal for two of them and another signal for the other two. And the other rule is also that the atoms joined either side of the CH2s can't have any hydrogens on them. And so the way this works is that we have two CH2s. And so these hydrogens would form a triplet. And these two hydrogens would also form a triplet due to the hydrogens on the carbon next door. And using the n+1 rule, and of course they're in a ratio of 2 to 2 because we have, and they don't have to be next to each other in the spectrum because, for example, if we had a carboxylic acid group attached to this one and an alcohol attached to this one, and then two hydrogens, then they'll be in different environments, and so that's why we get two different peaks, which aren't necessarily going to be next to each other. And then thirdly, looking at the CH3CH, this produces a doublet and also a quartet in a relative intensity ratio of 3 to 1. And again, they don't have to be next to each other. And the atom joined to the other side of the CH can't have any hydrogens on it unless they don't couple. So, for example, again, the OH group or an equivalent CH. So again, looking at this, what we have is that we have CH3 and then CH. And so these hydrogens will produce a doublet because we only have one hydrogen on the carbon next door. And this hydrogen will produce a quartet peak. And this will be in a ratio of 3 to 1. And again, they don't need to be next to each other because depending on what they have on either side, they'll be in different environments. And then now looking at the methyl group, this is another really important one to try and recognize. And this will produce a singlet peak with a relative intensity of 3. We don't actually compare it with anything, so we don't have a ratio. And the rule is that the atom joined to this CH3 cannot have any hydrogens on it. And the reason we get this singlet is because if we have a look at this methyl group, so we have a CH3 group, and these three hydrogens are all in the same environment because they're all attached to this carbon. And so we form a singlet peak because the rule is that the carbon joined to this carbon can't have any hydrogens on it. And so, for example, we could have a carboxylic acid group, and this would work. So this is how we would find a singlet. And then lastly, looking at the OH group, this will always be a singlet, and it'll have a relative intensity of 1 because there's only one hydrogen. And the rules are that a singlet for one hydrogen is usually an OH on either an alcohol or a carboxylic acid. And this hydrogen doesn't usually couple to other hydrogen atoms, even if there's an hydrogen atom on the next carbon atom. And so it remains as a singlet, and any hydrogens on the next carbon atom are not split by the hydrogen of the OH. So basically it's just by itself, and it doesn't affect anything, and other things don't affect this hydrogen. So what we have is, for example, we can look at ethanoic acid. So we have CH3 and CH2 OH. So this hydrogen here is going to be a singlet peak because it's not attached to a carbon directly, and so we don't have an adjacent carbon, and so nothing will affect this peak. And the relative intensity will be 1 because we've only got one hydrogen. So this is actually one of the easiest ones to recognize because it'll always form a singlet peak with a relative intensity of 1. So now we're going to look at an example. So here we have this molecule at the top. So we have this CH2 group here. And we've just learned that we form two triplet peaks, which won't necessarily be next to each other, but in this case they are, just because of the environments they're in quite similar environments. And so they actually turn out to be next to each other, but this isn't always the case. And what we need to notice is that the two carbons which are next door to these CH2s don't have any hydrogens on them. And then also looking at the CH3, CH2 here, these are completely separate to each other. They're not together at all. And this is because the CH2 is much closer to the oxygen compared to the CH3, and so they're in different environments. And they're in a ratio of 3 to 2 because we have 3 in the CH3 and then 2 in the CH2. And the splitting pattern is a quartet and a triplet. And then finally we have this CH3 here, which is a singlet peak because the next door carbon doesn't have any hydrogens on it, and there's 3 hydrogens which are in this environment, and so that's why we have a relative intensity of 3. And so this makes it a lot easier for us to work out what the structure of this compound is if we can find all of these different groups. So now we're going to have a look at how to predict the structure of compounds using its Proton NMR spectrum. So this first example is asking us to deduce the structure with molecular formula C6H12O2 using its Proton NMR spectrum. So the first thing I like to do is to have a look at the ratio of the relative intensities. So sometimes they give it to us in decimals, and so I quite like to convert them so I know how many hydrogens I have in each different environment. So we have 0.8s and 1.2s. So converting this means that we have a ratio of 2 to 2, 2, and then to 3, and then to 3. And this should add up to our 12 hydrogens, and it does. And so this is what the ratio is. So we have 2 hydrogens, and then 3 hydrogens, and 2 hydrogens, 2 hydrogens, and 3 hydrogens. And this makes it a lot easier for us because now we can see how many hydrogens we have in that particular environment. So what I'm going to do is just make this scale a bit more clear. So we've got 2 here and 4 here, and the scale goes up in 0.2. So we have 0.2, 0.4, 0.6, and then this is our 3. And what I do now is work from left to right with all of these numbers that I found, and I'm going to just write down where this peak is with regards to its chemical shift value. So delta measured in parts per million. So I'm going to work from left to right. So the first peak we have is a triplet peak. The chemical shift value is 3.5 ppm. And then for the next peak, a singlet. So this is the one which 3 hydrogens are in this environment. So we have a singlet, and we have a ppm value of 3.2. Another triplet peak, and this has a ppm value of 2.6. And then we have a quartet, and this is at 2.5. And then finally we have another triplet peak, which is at 1. So this 2.5 is actually kind of maybe 2.4. So now I've written it all out, it should be easier to see. So firstly, I'm going to work with this singlet here. I like to choose the one which is kind of the most different, because a singlet's quite easy to work with, because you know that the carbon next door can't have any hydrogens on it. And so this must be a methyl group. So this indicates to me that this is a methyl group. So you've got a CH3 group. And then we've got something next to it, but it can't have any hydrogens on it. And now looking at the data booklet, this value of 3.2 ppm corresponds to a hydrogen attached to a carbon, which is then attached to an oxygen. And this would make sense with our idea that whatever's attached to this carbon doesn't have a hydrogen on it. And so I think that it's very likely that this is attached to an oxygen. And so this is the kind of part of the compound that I think fits in with this part of the spectrum, this peak, because we have a relative intensity of 3, meaning that we have 3 hydrogens, which I've got here. We have a singlet peak, which means that we can't be attached to anything that has any hydrogens on it. And also we have a peak at a chemical shift value of 3.2, which corresponds to this CH3 group being attached to an oxygen. And now, using the table we looked at before with some common signals, we actually have 2 triplets, and we have the ratio of 2 to 2. So this implies to me that we have a CH2-CH2 group, because for example, if we took the carbon on the left, the 2 hydrogens on it, that would produce a triplet peak, because the adjacent carbon has 2 hydrogens on it. And if we looked at the right-hand side carbon, for those 2 hydrogens, they would also have a triplet peak due to the left-hand side carbon having 2 hydrogens on it. And so we would have the relative intensities to be in the ratio of 2 to 2, because we have 2 hydrogens on each carbon, and also 2 triplets. So then looking at our data booklet values for the chemical shift, we've got 3.5 and 2.6, and that corresponds to one of the hydrogens being attached to a carbon with an oxygen, and the other hydrogen being attached to a carbon with a double bond oxygen. And so I can kind of guess that one of these would be attached to an oxygen and the other one would be attached to a carbon with a double bond oxygen. And now looking at the quartet and the triplet, these 2 are also in the common signals table that we looked at. And so what these 2 tell me is that we probably have a CH3-CH2 group. because we have the ratio 2 to 3, and we have 2 hydrogens on one carbon and 3 hydrogens on the other, and we also have a quartet and a triplet. Because if we look at the hydrogens on the left, if we look at the carbon adjacent, there's 2 hydrogens on there, and so they would form a triplet peak, whereas if we looked at the right-hand side carbons, on the left we have 3 hydrogens, and so they would form a quartet peak. And now looking at the data booklet values, we can see that the 2.4 ppm corresponds to a hydrogen which is attached to a carbon which is attached to a C double bond O. And so I would guess that we have a C double bond O here. And so now we can actually build up the molecule, because we've now figured out the separate structures we have from this NMR. So all we need to do is just piece everything together. So what we have is, I'm going to start off with this. So we have CH3, and then CH2, and then I've got a C double bond O, and this looks a lot like this, but flipped the other way around. And so next to this C double bond O, I'd have CH2, and then another CH2, and then I'd have an oxygen, and then I'd have this CH3 here. And this would be our molecule. So looking back at the spectra, we can see why this is the case. So to check, we have these 3 hydrogens being in the same environment. And then we have these 2 being in the same environment. And then we have these 2 in the same environment. And then these 2. And then finally, these 3. And so that means we would have 5 peaks, which we do in our spectra, because we have 5 different environments. And now looking at these yellow carbons, they would produce a triplet peak, because we have 2 hydrogens on the carbon adjacent. And so then looking at the data booklet values, this would correspond to a ppm value of 0.7 to 1.2. And then for these hydrogens, we have a quartet peak, because we have 3 hydrogens on the carbon adjacent, and then because it's attached to a C double bond O, they will have a ppm value between 2.1 and 2.6. And then for these hydrogens here, we have a triplet peak, because we have 2 hydrogens on the carbon adjacent, and then because it's attached to the C double bond O again, we have a peak between 2.1 and 2.6. And then we also have these 2 hydrogens, which will also form a triplet peak, but they'll be at a different place, because it's in a different environment to the 2 before. And so this would have a ppm value between 3.1 and 3.9. And then finally, these hydrogens here, we have a singlet, because we don't have an adjacent carbon, and we should have a peak between 3.1 and 3.9 again. And also we can look at the relative intensities. So this would be 3, and then 2, and 2, and 2, and 3. So now looking back at the spectra, we can see that this is the case, because we have a triplet between 0.7 to 1.2. So that would be this one here. And then we have a quartet with a relative intensity of 2 between 2.1 and 2.6, which is this one. And then we have a triplet with a relative intensity of 2 between 2.1 and 2.6, which is this one here. And then we have a triplet again with relative intensity of 2, but this time between 3.1 and 3.9, which is this one. And finally, we have the singlet, which has a relative intensity of 3, and it's between 3.1 and 3.9 ppm. So this peak must be the one which represents this these 3 hydrogens. So really useful tips are to firstly look at probably the singlets, because they're the easiest to work with, because you know that the next door atom doesn't have any hydrogens on it. To remember the common signals, so when we have 2 CH2s together, or CH2, CH3. So for the 2 CH2s, we get 2 triplets with the ratio of 2 to 2. And if we have a CH3, CH2, then we have a triplet and a quartet with a ratio of 3 to 2. So we're going to look at another example, and this time we're trying to deduce the structure of the compound with molecular formula C8H15OCl using this NMR spectrum that we've got. So again, the first thing I do is convert all the relative intensities into whole numbers, so I can see how many hydrogens we have exactly in each environment. So we can divide all these by 0.3, and so we get 1, and then 2, 3, and then 9. So now we have the relative intensities, and these should add up to 15, like we have in the molecular formula. And now the first one I look at is probably the 9, because it's a singlet, and it's also got relative intensity of 9, and so that gives me a really big clue as to what this part of the structure would look like. Because the only way we can have 9 hydrogens being in the same environment is if they're all on the same carbon. So if we have 1 carbon, and then we have CH3, CH3, and CH3, now all of these hydrogens are in the same environment, and they're going to be a singlet, because the carbon they're attached to, the carbon which is adjacent to the one it's attached to, won't be attached to any hydrogens. And so I've already worked out this part of this compound. And now I'm going to look at this singlet here. And it's also important to note, actually, that the singlet with the relative intensity of 9 is at a chemical shift value of 0.8. And it's a singlet. And so for this singlet that we have, which has a relative intensity of 2, this has a chemical shift value of 2.2, and it's also a singlet. And then for the doublet we have with a relative intensity of 3, it's got a ppm value of 1.4, and like I said, it's a doublet. And then for the last one, we have a quartet, and this is at 4.6. So it's always helpful to work these out either as you go along, or maybe at the start, to just help you work out what you've got in that part of the structure. So now looking at this singlet peak, what we can see that 2.2 actually corresponds to a hydrogen which is attached to a carbon, which is attached to a carbonyl. And we also have a singlet with 2 hydrogens in this environment. So this would make sense if we had something attached to a carbon with these 2 hydrogens, and then we had a C double bond O attached. And the thing on the left of this carbon here won't be able to have any hydrogens on it, because then we wouldn't get a singlet peak. And so this is what I would guess this part of the structure would look like. And now looking at this quartet, this means that on this 1 hydrogen, we must have a CH3 group, because we must have 3 hydrogens next door. And so we can guess that this part of the structure would have this CH, so this would be our hydrogen. And then next door, we would have to have 3 hydrogens. And the only way we can have 3 hydrogens is if it's at the end of the structure. And then this left-hand side carbon can't be attached to anything else with a hydrogen on it. And now we guess, using the molecular formula, that we have a chlorine attached here, because we have to have something attached, and we can't have an oxygen attached because we can't have a single bond to an oxygen. And so we guess that it should be a chlorine. And looking at the data book, this looks like it could be feasible, because if we have an R group, a CH2, and then Cl, the hydrogens would have a chemical shift of around 3.1 to 4.2, and this is 4.6, which is slightly higher, but it looks like it could work. And then finally, looking at this doublet here, this actually refers to the 3 hydrogens here. Because if I have CH3 and then CH and then Cl, for the 3 hydrogens, because there's a hydrogen on the carbon next door, we form a doublet peak, and we have 3 of the hydrogens in this environment. And also, when we look at the chemical shift value of 1.4, corresponds to 3 R groups attached to a carbon attached to a hydrogen. And if we look at the data book value for 1.4, this corresponds to an R group, 2 R groups, and CH2. And so this looks like it could work. And so now we can start to build up our molecule. So we have CH3, so I'm starting off with this one, and then I have a hydrogen and a chlorine, and then I can put in this section here. So we have a C double bond O, and then CH2, and then we have a carbon with the 3 methyl groups. And this is our molecule, and it should work, because as you can see, we have 3 of these in the same environment, and then we have this one in an environment by itself, and then we have these 2 which are in the same environment, and then finally we have these 9 hydrogens which are in the same environment as each other. And so that means we have 4 peaks which we do on the spectrum. And so we have that these 3 hydrogens on the end produce a doublet peak. So it would be this one here. And then the hydrogen, which is coloured in red, this would form a quartet peak. So it would be this one over here. And then we have the green hydrogens, which would form a singlet peak because it's not attached to any carbons with hydrogens on them. And they're also next to a C double bond O. And so we should have a ppm value between 2.1 and 2.6. And so it'll be the one here. These 9 hydrogens, which will form a singlet peak because, again, they're not attached to any carbons with hydrogens on them. And so this peak here corresponds to these 9 hydrogens. So this should get easier once you start doing more and more of these types of questions. But it is quite hard to think of things that could work for the peaks of the spectrum. But just keep trying to work out different sections. So firstly, we look at the ratios, and then maybe write down all of the chemical shift values and what type of peaks they are, and then try and use the table that we looked at of common signals to try and help you identify if you have sometimes 2 CH2 groups or CH3 CH2 groups. For this example, it's a bit harder because we actually didn't have any of those except for the 3 methyl groups that we had on the carbon. And that's quite a nice one to remember, because that's the only way that we can have 9 hydrogens being in the same environment and also for it to be a singlet peak.